bright and early tomorrow morning. Send me an email, and I'll do my best to get back to you.
The test is at 1 for all of us, right?
It's at 8 a.m. You got plenty of time. You guys are golden. Plenty of time. These are the topics that are generally covered in the second half of the course. Optimization, Lagrange multipliers, double integrals, changing the order of integration, and integrals in full. Is there anything on here that you don't think is on the test, or not on here that you think is on the test? Yeah.
Integration by parts.
You might. I don't remember specifically if they do that, but it's always good to know how to do integration by parts. I don't think I have an example in here that you need integration by parts, but I might be able to. Use substitution. I don't have an integration by parts, so we'll do use substitution, and I can probably make up an integration by parts. Yeah, so is there anything else that is missing or is extra? No? Okay, cool. So I don't have any copies of the final because they don't let us keep them. So this is all just going off of, these are questions that I've gotten from homeworks, from self-studies, from past years, stuff like that. So they should be accurate to what's going to be on the test, but it's not going to be as specific as this is a test question from last year. From what I heard from the midterm, that didn't help anyways. So anyway, first thing that we're going to start off with, is there any one topic that's like the worst? Optimization? Lagrange? Lagrange is normally a pretty difficult one because you throw lambda in there. You guys are going to hate lambda. You get to deal with that in diffie-q and multi, just different facets. Lambda is just the base of your existence.
Critical points?
That's in optimization.
Okay.
So I'm finding those critical points. Okay, so without further ado, we'll get going on some optimization. So optimization, the good thing is it's broken down into a couple steps. I mean, actually doing those steps is where it gets difficult, but it's broken down into a couple steps that you can kind of use to guide yourself through the question. And if I need to write bigger, let me know, because this room goes pretty far back. So we got, this is finding critical points within a region. So it's going to give you some function that defines a shape. It's going to give you some region that's the boundary zone, and it wants to know what's the max and min inside this shape or on this line, something like that. So the way that you do that is first you take the function that you're trying to optimize, and you find both first order derivatives, so f with respect to x and f with respect to y, and set them equal to 0. So that's one type of question that it can ask within optimization. Another type of question that it can ask is finding critical points of each boundary line.
Let's see. Zach, are you comfortable with that?
And then, so the question could ask you to find one of the 3 of these, but most of the time it's going to be each of these 3 is part of one problem. So it's going to ask, first you have to find, or it's going to say find the global min-max within this region. So the first you have to find the critical points within the region, then you have to find the critical points on each of the boundary lines, and then knowing all of that, find out what the global min-max is. And that's just looking what number gives you the highest high and the lowest low. So these are going to be the 3 main steps of solving your optimization problem with finding your critical points. So I'm going to do a little side note with the second derivative test, because the second derivative test is how you identify if it is a maximum, a minimum, or a saddle point. So maximum is pretty clear, it's the highest. Minimum is pretty clear, it's the lowest. What is a saddle point? Anybody have any clue what a saddle point is? What's a saddle point? Okay. So, yeah, it's called a saddle point because it makes a saddle. So I've tried drawing this in the past and it's kind of come out very poorly. So just think of a Pringles chip, okay? If you put a spot right in the middle, so I'm thinking of the chip, it's like up on the sides, kind of like that, but then in the middle it curves like that. So if you look at it from one way, it's the maximum going this way, because it's at the top of that peak, but it's at the bottom of this peak. That's what a saddle point is. If you look at it in one direction, it's at the maximum. If you look at it in the other direction, it's the minimum. So that's the idea of what a saddle point is. And that's how it differs from a minimum, which is at the bottom of both, and a maximum, which is at the top of both. So the way that you classify those, I want to write two as well, so I'm just going to write those here. So you have our second derivative test. And what the second derivative test tells us to do is we take this formula. D is equal to the second derivative with respect to x evaluated at a point AB times the second derivative with respect to y evaluated at a point AB minus f with respect to x with respect to, so fxy evaluated at AB squared. This is, so you do the second derivative, second derivative, second derivative. You multiply these together, subtract that, and square, and that gives you some value d. Now this value d, if d is greater than 0, and your second derivative with respect to x is greater than 0, you have a relative min. If d is greater than 0 and fxx is less than 0, you have a relative max. If at any point you get d to be less than 0, you have a saddle point. And if you have d equal to 0, we don't know what's going on. So I'll just hope that doesn't happen. So when you evaluate this, you get something for d. You look at this first column first. Is d greater than 0? Yes. Now look at fxx. Is it greater than 0? It's a relative min. If it's less than 0, it's a relative max. And that's how you determine if some point that you get is a minimum, maximum, or a saddle point. Min, max, saddle point. So with that, I'm going to jump into a problem that's kind of going to use all of this and make it a little bit more clear. We're going to start over here, and then I'll have to work back over there and write some stuff. But it starts off by saying, find the critical points of f of xy is equal to x squared y plus 2y squared minus 8xy plus 11, and classify them. So now this one doesn't give us any boundary that we have. It's just saying this is our function, what's the overall min and max. So this second step isn't going to be involved in this one because there is no boundary line. But we can still find the critical points in a region. In this case, the region is everything. So we follow the same steps that it says for finding critical points. We take our f of x and we take our f of y. We set it equal to 0. So my f of x is this. I'm just taking my derivative, treating x as a variable, y as a constant. So I have 2xy, that goes to 0, minus 8y, that goes to 0. I'm going to take my f with respect to y. I get x squared plus 4y minus 8x, and again, that goes to 0. So now I'm going to set each of these equal to 0, and I'm going to solve. So I do this one first. I see there's a y in each term, so I'm going to factor that out. And I get 2x minus 8 is equal to 0. So y times 2x minus 8 is equal to 0. And I know that this is just y times 2x minus 4 is equal to 0. So I look at what statements or what values for x and y make this true. So I know if y is equal to 0, this is true. Or if x is equal to positive 4, this is true. Now I come over to my f and y, and I try and factor this. And I now have x squared, but I have x's and y's. So what I'm going to do is I'm going to take my answer for this. I'm going to say, OK, assuming y is equal to 0, what do I get for x? Because that way I'll get a point for a maximum, which is what, or maximum or a minimum or a saddle point, which is what I need. I need an xy coordinate. So I'm going to say, assuming y is equal to 0, that leaves me with x squared minus 8x is equal to 0. This I know how to solve. I factor out an x. I get x minus 8. So x can equal 0, or x can equal 8. So now I know two critical points that I just found are x is equal to 0, y is equal to 0. So we have one critical point is 0, 0. I have another one that's 8, 0. And now I'm going to plug in the other thing that I found over here is that x is equal to 4. So now we assume x is equal to 4, and we restart it. So if I plug in 4 here, I'm going to have 4 squared, which is 16, plus 4y, minus 8 times 4, which is 32, is equal to 0. So now I have 4y, combine these, minus 16 is equal to 0. So 4y is equal to 16. So we have 4y is equal to 16, which means y is equal to 4. So my third critical point is x equal to 4, y equal to 4. So these are my three critical points. This is where I'm going to have either a maximum, a minimum, or a saddle point. Now, the question asks us, find all the critical points. We got them. Now we need to classify them. So, I'm going to erase this. I'm going to make this fit right here. So, in order to classify them, I need to do this formula right here. So f with respect to x, or f sub xx times f sub yy, then f sub xy squared. So first I need to find what those are. So I'm taking f with the second derivative with respect to x, and that's just taking the derivative of this with respect to x, which is just going to give me 2y. Then I do the same thing with f sub yy, and I get 4. Then I do f xy, and you can either take this and take the derivative with respect to y, or take this with the derivative with respect to x. You're going to get the same outcome either way. So I'm going to do, so the derivative of 2xy with respect to y is just 2x. And then minus 8. So these are my three values. Now I have to evaluate them at some point A, B, and that point A, B is these three critical points that I found over here. So I'm going to plug the first one in. When I plug in 0, 0, my fxx is equal to 0. When I plug in 0, 0, this is equal to 0. 4, no matter what, is going to be equal to 4. And 0 minus 8 is equal to minus 8. So when I do my D, I'm going to have f double x times y. So this is just going to go to 0, and it's going to be minus this squared. So this is going to be 64. Negative 8 squared is 64. You have a minus out in front. So this is negative 64. 64, which if I have a D less than 0, I know this is a saddle point. So this is, we have 0, 0 is a saddle point. Does that make sense? Cool. Now we're plugging in our next point. And my next point is 8, 0. So when I plug in 8, 0, this is still 0. This is still 4. 2 times 8 is 16, minus 8 is now positive 8. So I'm going to get 64. Again, there's a minus out in front, so this is again negative 64. So I know that 8, 0 is also a saddle point. Then I'm going to plug in my last one, which is 4, 4. I'm going to get 8. 4 is still 4. And I have 2 times 4 minus 8, which is going to be 0. So now looking at this, I'm going to have 8 times 4 is 32, minus 0 squared. So this is going to give me 32. So I look over here, if D is greater than 0, I now have to look at fxx. fxx is positive, so I know that this is a relative minimum. So I know that 4, 4 is a relative min. Does that make sense? And what relative minimum means is if you're standing at that point, no matter which direction you move in, you're going to be going up in elevation. Same thing with the relative max, they're always going to be going down. So this is a good example of how to do this first step. Because this problem didn't have any boundaries. This one was just find all the critical points, identify what they are. Now I'm going to go into a problem that does have the boundaries, and it asks for the global min and the global max. So I can tell how nervous you all are for this final tomorrow because it was dead silent the entire time. And it's not that bad. Think about it. Even if you fail this one, you just retake it again next semester and you're not behind it all. You're just with everyone else.
That does not make me feel better.
That's the worst case scenario. Right? It's not that bad.
That's so bad.
But you're not going to be behind. You're not going to be that like third year that's still in like freshman level classes. You're still going to be a freshman in a freshman level class. That's the absolute worst case scenario. And even if you fail this test, odds that you fail for the whole course are very small. It's not that bad. Deep breath, ready? Okay, we're all going to take a nice deep breath. In through the nose, out through the mouth. Ready? Ready? One more. We're all going to be okay.
That's because you got 6:30.
Okay, so now we're going to do this next problem. And this one asks us to find the absolute min and max. So find absolute, min, and max of, we have f of x, y is equal to 3 plus xy minus x minus 2y in the region with vertices of 1, 0, 1, 4, and 5, 0. So it's giving us the vertices of some region, so it's not even giving us the formulas or the lines to define it. And it's saying this is our formula, find the absolute, or in other words, the global min and max. So what's the first step that you think we should do? Graph it. I like that. Because it's giving us just 3 points. I don't have any region. Let me make my region first, so that way I can look at it and see first what kind of shape I have. Hopefully you know what shape I have, because there's only one shape that has 3 points. But, okay, so the first thing we're going to do is we're going to graph it. I'm not going to do this I'm not going to do it to scale, but we have 1, 0. So 1, 0 is about right there. Then we have a 1, 4, which is about right there. And we have 5, 0, which is about out here. So you connect the dots, and we got ourselves a right triangle. Right? So that's my region that I have. So imagine this function, this 3-dimensional function is some sort of shape, and we're now cutting it into that one triangle, and we're looking what's the highest point, what's the lowest point, what are the saddle points. Or saddle, no, it's not, it just wants to know what's the highest point on the shape in this region, what's the lowest point in that region. That's all it's asking us to do. So, first thing that we do the same thing that we did in our last problem. We want to find the critical points inside the region, so that's in this whole space right here. We want to find, ignoring the boundary lines, we want to find the highest point inside. So the first thing that we're going to do is find our fx, our fy, set them equal to 0. So f with respect to x, that goes to 0. That's just y. Minus 1, that goes away. That's nice and easy. F with respect to y, that's 0. That's x. That's 0. We have minus 2. Not that bad, not that bad. We're good at our first derivatives, right? We got those on the last test. We're good with those. Right? Yeah. Cool. So we took our fx, we took our fy. Now we're going to set them equal to 0. So we set that equal to 0. We set that equal to 0. These, piece of cake, I knew these in 8th grade. This is y equals 1. This is x is equal to 2. So this one's good. We don't even have multiple points. We just got one point within this region where fx and fy are both equal to 0. So some critical point 2, 1, the first thing you want to do is make sure it is within that region. So we know this is 5, 0. We know this is 1, 0. And we know this is 1, 4. So is the point 2, 1 within that region? Yeah. So we know this is a good critical point. So critical point is 2, 1. I'm going to list them all there if we find more. So that was the first step. The next thing that we want to do is find the critical points on each of the boundary lines. So we found everything inside. Now we want to find the critical points for each line. So you might be saying, how are we going to do that? Well, let's start, pick one of the lines. Which one do we want to do first?
Hypotenuse.
I heard a lot of different things.
I heard hypotenuse.
Okay, we're not going to do that one first because that's the hardest. So we're going to do either the vertical or the horizontal. Vertical, I heard vertical. So the vertical line who wants to give me a good way to write that as a line? X equals 1. So we got x equals 1. That's a line that we got going on. So I'm going to plug in 1. Because I know anywhere on that line my x is equal to 1. So I have f of 1 comma y is going to be equal to 3 plus y minus 1 minus 2y. So simplifying that a little bit, we have f1 comma y is equal to 3 minus 1 is 2, y minus 2y is minus y. So we have f of 1 comma y is equal to 2 minus y. So we now need to look at that line. This is what the function looks like along this line. So we need to see what is the maximum that this function can have, bounded by the lowest y value we can have is 0, the highest y value we can have is 4, because that's what the two endpoints of that line are. So we know that we're looking between 0 and 4 for this y. So anytime you have a straight line, so your variable is to the first power, we know that the max and the min are going to be at the two endpoints. Because if you have something going straight up, one side is going to be the highest, one side is going to be the lowest. If you have a quadratic, you then have to start worrying about it in the middle, because it can go up and down and do some weird shit. But if you have one straight line where that's to the first power, you know only the endpoints matter. So I'm going to look at this, and I'm going to plug in 0 for y, then I'm going to plug in 4 for y. One of those is going to be the maximum on that line, one's going to be the minimum. So if I plug in 0 for y, I'm going to have f of 1 comma 0 is equal to 2 minus 0, or 2. Now if I plug in 4, I'm going to have f of 1 comma 4 is equal to 2 minus 4, which is negative 2. Now those are my two relative mid or critical points along that line, where this one is a maximum, that one's the minimum. Yeah?
Are we always going to get a right triangle?
I mean, I can't even guarantee you're going to have a triangle. Because like I said, this is something that I found on either one of the self-studies or one of the homeworks when I was in the class. They're not going to give you something where there's two lines that aren't straight. Like two lines, because like in this situation we have one line is x equals something, and one line is y equals something. And then the third one you have to do a little bit of trickery with. I very much doubt they're going to give you like an isosceles triangle where two of the lines aren't along the grid. Does that make sense? Now, it's the final and you have 4 hours, so they could, but I doubt they're going to, because as they're not nice people, but they're mean. They're not mean people. Okay? They're not nice, but they're not mean. So they're testing you on this one diagonal that you know how to do the diagonal line. They don't need you to do it for 4 lines to prove the same thing. If you get it the first time, you're good. If you don't get it wrong the first time, then they know you don't know. But multiplying it by 4 isn't going to benefit them any. So I doubt they're going to give you more than one diagonal line. Now, whether that means they give you a 4-sided square that's all straight and just more sides you have to test, they could do that. Or they could just give you a right triangle that works like that. I can't say. They can do whatever they want. Yes?
Wait, they did? Did they? Or you theoretically?
Did they have a problem with R?
Oh, yeah.
The only thing is,
dodecahedron, like make it like a 3D shape.
yeah. So let me just look.
I just skipped that problem till the last 5 minutes and just like.
That's the last 5 minutes.
I did it on the last test and I actually got the question like 8 out of 10 points. What do you have to get to pass this class?
That's not what I'm looking for.
Really? You just need 40? And then 60% is the 2 terms. Dude, the curve last time was so nice.
I think I'm gonna get up. Is it the same person?
I hope. Because I got a 66 on last final. Oh, gone. This is like phased out.
So the good side is if those tests are, if it's going to be similar to those tests, then this is pretty accurate to what's going to be on it. There are 2 tests from 2013, which was like before they changed the class, but the 1 test from 2014 is very similar to the stuff I have on here and the stuff that I actually had on the midterm review that wasn't on your midterm. But I've been told that this is going to be more similar to past finals than your midterm was to past midterms.
I hope so.
So that's looking good.
I mean, they like lying to us. You know.
Yeah, that's what they do. But anyway, back to the problem we have right now. What we found was we found a maximum and a minimum along that line given that function. So we know that this is at point 1, 0, and this is point 1, 4. So those are also critical points. Now, we did this one line. Now we got to do the next line. So we're going to do the horizontal because that's nice and easy. We can just say y is equal to 0. So, starting that off, we're going to say f of x comma 0 is equal to, and now we're just going to be, again, rewriting this function, but with y being equal to 0. So this is just going to be 3 plus 0 minus x minus 0. So we just have that. Now again, we have x to the first power. So what does that mean?
Endpoints are going to be either a max or a min.
Endpoints are what matter. Those are going to be either our max or our min. So again, we're just going to plug in our endpoints, and you have to figure out what those endpoints are. So looking at that horizontal line, we know that x is going to fall between 1 and 5. Because those are the x values of the 2 endpoints. So we're going to plug in 1, and we have f of 1 comma 0 is equal to 3 minus 1 is 2. F of 5 comma 0 is negative 2. And again, these are our max and our min. And one thing that you should check is f of 1, 0 should equal f of 1, 0. If it doesn't, you messed up somewhere. But since we got 2 and 2, we know that makes sense. So these are 2 more points that I have. From testing that bottom line. Now we got to test our last line. And our last line is a little bit more tricky because we can't just simply sub in x is equal to 1 or y is equal to 0. We have to get a little bit more fancy. Because looking at this line, what's a way that I can represent it? So I know that the y-intercept, it's got a slope of negative 1. Because it goes, if you do the math, you can figure that out. It's got a slope of negative 1. The y-intercept is going to be 5. So I know the formula for this line is y is equal to negative x plus 5. So I'm going to take that formula and I'm going to plug it in to my f of x, y. So this is going to be f of x comma x, or negative x plus 5. Because all of my y's, I'm plugging in negative x plus 5. So we're going to have 3 plus x times negative x plus 5 minus x minus 2 times negative x plus 5. And what the purpose of doing this is we're eliminating the y variable. Because if we can get rid of our y, we know how to solve for the we know how to optimize for one variable. It's something that we've been doing for a while now. So we're going to simplify this. This is going to be 3 minus x squared plus 5x minus x plus 2x minus 10. Combining some like terms, we're going to have negative x squared plus 5x minus x is going to give me 4x plus 2x will give me plus 6x. 3 minus 10 is negative 7. So now I'm just left with basically an f of x is equal to negative x squared plus 6x minus 7. So since I'm down to one variable, I can just look at this diagonal line. What are my bounds for this line with respect to x, because that's the only variable that I have. So on the left side of this diagonal, I have 1. At the right side, I have 5. So I know my x has to be within the bounds of 1 to 5. However, I have an x squared. So I don't know for sure that my endpoints are going to be what matters here, because I could have a peak in the middle. So what we have to do is we have to find the critical points of this line. The way that we do that, we take the derivative, we set it equal to 0, just like we've been doing for back in like pre-calc days. So we have our f prime is going to be equal to negative 2x plus 6. Set that equal to 0, and we get x is equal to 3. Now, if we have x is equal to 3, then we know that our y is equal to negative x plus 5. So we plug in that 3, and we get our y is equal to positive 2. So we did that because we had to check if there was a maximum, or we need to find the maximum and minimum within that line. But then we also have to test the endpoints. So now we have to test the endpoints of 1, 4 and 5, 0 to see if those are bigger or smaller than anything we've got so far. So I'm going to do that right over here. So we have f of 1, 4. And to save time, we already know the value of that endpoint, because we've already plugged in 1, 4. That gives me negative 2. And then we have f of 5, 0. And we already know the value of that is negative 2. And the value of this point that I found right here, we have to plug in that 3 and 2. So we have f of 3, 2 is going to be 3 plus 6 is 9, minus 3 is 6, minus 4 is 2. So now we got a bunch of coordinates that give us a bunch of different max and mins. We started off by finding something inside at the point 2, 1, which is somewhere in there. And we know that at this point, actually we never found the max. If we were to plug this in to find the value of the function at that point, we would have 3 plus 2 is 5, minus 2 is 1, minus 2 is negative 3. That doesn't sound right. 5 minus 3 gives me 2. No, it's 3. Minus 2 is 1. Is that right? Okay. So when we plug this in, we have f of 2, 1 is equal to 1. So we have this critical point of 2, 1. The value of the function is 1. We have the critical points 1, 4, 5, 0, 3, 2. We get -2, -2, 2. Looking at all the points we've gotten, the highest value of the function that we have is +2. The lowest value of the function that we have is -2. So those right there are our absolute max and our absolute min. If it asked you to tell us the location of those points, you would then have to list, well, this is the absolute max is equal to at locations 3, 2, 1, 0, 1, 0, anywhere else that we've gotten at. But it doesn't ask for the locations, it just says, what is the absolute max, what is the absolute min? So I then write my max is equal to 2, my min is equal to -2, and that's your final answer right there. Because we tested, we found all the critical points inside the region, we found the critical points of each boundary line, and we found the global min-max by looking at all the points we found and seeing what was the highest, seeing what was the lowest. Question to that.
Should you always just test the vertices too?
Well, by testing the endpoints of each line, we tested the vertices. Because we ended up testing 1, 4, 1, 0, and 5, 0 by testing the endpoints of the line.
Yeah,
So-
but no, what I'm saying is, can't you do that without having to do, because those just are the endpoints that you had, all the points that you found from testing the endpoints, couldn't you just test the vertices and not have to do one? Oh,
This is the one situation that makes it different, because if one of those lines ends up having a quadratic, like a x squared or an x cubed, like the function defined on that line is not linear, then you might have a maximum within the line, so you'll have to test that in addition to the endpoints. That's the one thing that you might miss if you only do the corners.
So just the hypotenuse, you know?
In this case, yes. In other questions, it might be more depending on what this function is. Like if this function gives you like an x squared in here, then all of them are going to be messed up. Are there any other questions on this one or optimization in general? If not, we'll go to our good old friend Lagrange. Lagrange time. We got some Lagrange multipliers.
If you use a 9 sign, it would be 0 minus points. You suck. Heracles. Second.
So as complicated as Lagrange multipliers seem to be and have been, that's all that matters. The way that you find Lagrange multipliers is you have your gradient of f, which f is your function that you're dealing with, is equal to lambda times the gradient of g, where g is what is the constraint that you're dealing with. So your boundary lines, your shape, whatever. That's all that matters. I know that sounds very simple, and I'm going to explain to you and show you in a problem how that applies. So jumping right into a problem that I found, I think this one was on one of the self-studies, I'm pretty sure. Good old Patrick JMT. You guys still do self-studies, right?
Yeah.
Oh, thank God. That's the only way I learned this. I'm telling you, Patrick JMT is the boy. But after Diffie Q is still helpful. After that, he doesn't have many videos on multi. So then you have to like start actually writing it. Okay. So it tells us find the maximum. Find the maximum and the minimum values of, we have f of xy is equal to 4x minus 6y with the constraint of x squared plus y squared is equal to 13. So the difference between this problem and the last one that we had, the last one, the problem gave us vertices. And we had to, it was broken up into 3 different functions with 3 lines that were our boundary. In this one, we have one boundary that's our constraint. It's one function that serves as a constraint for the whole problem. So anytime you have one function as your constraint, this is when you're going to be using Lagrange as opposed to just testing each line. So I'm looking at your gradient of f is equal to lambda times the gradient of g. So gradient, somebody might not remember from the first half, but gradient is just f with respect to x, f with respect to y, f with respect to z, if you have that many values. So first I'm going to find my f of x, my f of y, then I'm going to find my g of x, my g of y, then I'm going to set f of x equal to lambda times g of x. Simple as that. And using that, we can eventually find what our lambda is. So first I'm going to find my f of x. So I just take the derivative of this with respect to x, gives me 4. Then I take the derivative of it with respect to y. It gives me negative 6. Now, how do I take the derivative of an equation? Because I have something on the right side of the equal sign, and I don't want to do that because it's going to make things a little weird. So what I'm going to do is I'm just going to subtract it over, because we want our g to be equal to 0 at all times when we take our derivative. So I'm going to say that my g of xy, the function that I'm dealing with, is just going to be x squared minus y, or plus y squared, minus 13 is equal to 0. And now this g of xy equals x squared plus y squared minus 13 is what I'm going to take my derivatives of. So I have g of x is just going to be equal to 2x. I have g of y is equal to 2y. And now I set my gradient of f equal to lambda times my gradient of g. So I come over here, and I have my f of x, which is 4, is equal to lambda times 2x. And I have my gradient, or my f of y is negative 6, is equal to lambda times 2y. And then looking at this, I have x, y, and lambda are my 3 variables. So I know I need 3 equations in order to solve it, this system. So my third equation is the function that I started off with as my constraint. So my third equation is, you can either do it this or you can do this. I'm going to write it as x squared plus y squared minus 13 is equal to 0. So now I have 3 equations, I have 3 variables, so I can solve this system. So the first way that I'm going to do it is I'm going to try and get everything in terms of lambda, so that way I can solve for what lambda is, and then everything else will trickle down. So I'm going to solve x equals something in terms of lambda. So the first thing we're going to do is I'm going to divide over this 2 lambda. So I have x is equal to 4 over 2 lambda, which is equal to 2 over lambda. That's my x. Now I'm going to do the same thing with y. I'm going to divide over my 2y. I have x is equal to -6 over, divide over the 2 lambda. And this is y is equal to that, which means -3 over lambda is equal to y. Now, knowing these two, I'm going to take this x, I'm going to plug it in there. I'm going to take that y, I'm going to plug it in there. So I'm going to have 2 over lambda squared plus -3 over lambda squared minus 13 is equal to 0. So this gives me 4 over lambda squared plus 9 over lambda squared minus 13 is equal to 0. So this is, I can combine like terms because it's the same denominator. So this is 13 over lambda squared is equal to 13. I can divide by 13 on each side. So it just becomes 1 over lambda squared is equal to 1, which means lambda squared is equal to 1, which means lambda is equal to plus or minus 1. Does that make sense? Now from there, I can go back and find out what my x and y are. So x divided by 1 is just going to give me 2. X divided by -1 is just going to give me -2. Do the same thing with y. I get y is equal to -3, and y is equal to +3. Now from here, I have 2 values of x, 2 values of y. I'm going to test each combination, find what the value of my f of x, y is, and then from that, I can determine what the maximum and the minimum are. So if my f of x, y is equal to 4x minus 6y, I know that if I'm going to do f of 2 comma -3, I'm going to have f of 2 comma +3. I'm going to have f of -2 comma -3. I'm going to have f of -2 comma +3. If I plug in 2 for x, I get 8 minus a -18 is going to give me +10. No, 26. I have these in a different order. 8 minus 18 is going to give me -10. -8 minus a -18 gives me +10. And a -8 minus 18 gives me -26. So this question asked me to find the maximum and minimum values of this function. I know my maximum is right here because I have a +26, and my minimum is right here at -26. And you can label it as max, min. Either way, that's the problem. Now I know this is probably simpler than you've had on your homeworks, that you've seen in your workshops and stuff like that. I didn't want to do a too sophisticated problem because I wanted you to see the steps and see you do this, then this, then this. If it's a more complicated problem with more complicated derivatives, or you don't just get constants here, where solving this is a little bit more difficult, break it up, think of it in parts. You know how to take a more difficult first derivative. So if going from there to here is tough, you know how to do that. If going from here to here is tough, you know how to do that. Then, when we have this and this, we set them equal to each other. And we just have 3 equations. Now, don't think of it in terms of, well, now I have a lambda in there and it's a long problem. Think of it as, I just have a system of 3 equations. It might be a little difficult to solve, but you know how to solve difficult systems of 3 equations because we're used to doing systems of equations. So you do that, and eventually you solve for one variable and you plug it back in to get the others. Now you're just left with some points. You just test each one by plugging it into your original function, and you get your answer. So will the